Hello, everyone, and welcome back. In the previous lecture, we defined work, and we used that in conjunction with Hooke's law to solve a number of physical problems involving springs. In this video, we're going to continue our exploration of work, but move away from springs and look at other physical problems where we can solve for the work required to move certain objects over large distances. So let's jump right in. Okay, so in this lecture, we're just going to do examples, two in particular. So let's go ahead, let's start with the first example. So example one here. In this case, we're given a 5 kilogram bucket. And it's lifted from the ground into the air by pulling in 20 meters of rope. At a constant speed. So you can imagine maybe this is put on a winch or something like that, and this is a perfectly constant speed that this thing is being pulled up that 20 meters by this rope. Sorry, at a constant speed. And we know that the rope weighs 0.08 kilograms per meter. So how much work was spent lifting the bucket and rope? Okay, so let me start with a little sketch of what we're looking at here. So we've got our little bucket. And this thing is on our rope. Yellow is supposed to represent a twine rope, maybe. And we are pulling this thing upwards. This distance that it's moving up is 20 meters. And then we know that the rope weighs 5 kilograms. We also know that the rope weighs 0.08 kilograms per meter of rope. So we're asked to find how much work is being spent lifting the bucket and the rope. So the way that we're going to approach this problem is we're going to break down, we're going to see how much work is required to lift the bucket, and then we're going to add in how much work is required to lift the rope. And you'll see as we go through this why we need to break it up. So in the case of the bucket, things are relatively simple. So the bucket in this case, we can find the force being exerted just using Newton's second law. So that is force is equal to mass times acceleration. So we know that the mass of the bucket is 5 kilograms. And the acceleration here is going to be the acceleration due to gravity. So that's the force that's pulling this rope down, right? If there was, or sorry, this bucket down. If there's no gravity, we wouldn't have to worry about any work being exerted here because there's nothing resisting our motion. And so that tells us that the acceleration is going to be 9.8 meters per second squared. So that's the acceleration due to gravity. So the force in this case is given by Newton's second law, mass times acceleration, which in this case is a fairly simple computation, right? This is 5 times 9.8. Sorry, 9.8. And that's actually equal to 49 newtons. So that's the weight of this bucket. And then we have to do the work. And this is weight times distance. So the force times distance. And in this case, we are moving a weight, a force of 25 or 45 newtons up 20 meters. So this is 45 times 20, which is equal to 980. And you should remind yourself that we have a specific unit of measurement for work when we're using these SI units, and that is joules, right? The Newton meters. Okay, so that was pretty straightforward. So let's see why we had to break up the rope from the bucket. So let's look at the rope now. Well, in this case, we have a mass for the rope, which is 0.08 kilograms per meter. So now we have to ask ourselves, how many meters of rope do we have? So if we're at a vertical height of y, so let's imagine, so the bucket is at a vertical height of y, and y in this case will be between 0 and 20, right? 0 meaning we're on the ground where we started, 20 meaning we're at the very top where we ended. So then this tells me that there is 20 minus y meters of rope out. So if you look at the picture, this distance right in here might be y, and then that tells us, making a little bit of an assumption that the bucket has no height. So there's a little bit of fantastical element going on here, but that's okay. We can make these assumptions. So that tells us that there's 20 minus y meters of rope out pulling this thing up. So that tells us that we can find, first of all, how much the rope weighs. So in this case, we have a weight of 0.08 kilograms per meter. So that means that we can find the number of kilograms by multiplying by the number of meters. And then we have the same acceleration that was pulling on the bucket. We've got that pulling on us. That's gravity. So the force in this case is equal to mass times, or mass per meter, sorry, times the number of meters, and then times acceleration. And this is all in newtons. And now we have a non-constant force. So we have to use that definite integral in order to compute for the work here. So the work is actually equal to, now we have an integral. Y is the distance that the bucket is from the ground. This is running between 0 and 20. So that means our definite integral goes from 0 to 20. And let me just put everything in. I'll clean it up in a moment, but I want us to really see that this is just the force being integrated over the space y. And now, if I clean this up a little bit, if I multiply everything out, expand it, I get 15.68 minus 0.784 y dy. And life is pretty good now, right? Because this is just a linear function. If we sort of ignore those ugly looking constants, this is just a line. And so that means that when we integrate it, we'll get a quadratic function. So this leaves me with 15.68 y minus now half of 0.784. So this is going to be 0.39, oh, I'm sorry, 392. Y squared, right? Because that's the y squared over 2 piece that's coming through. And then going from 0 to 20. And in this case, it's just plugging in upper and lower bounds. So this leaves me with a nice 156.8 joules. And so that shows us that the work done to move the bucket was 980 joules, and the work done to move the rope is 156.8 joules. So therefore, the total work, this is the bucket plus the rope. Sorry, I didn't mean to put a decimal in there. And this gives me 1136.8 joules. Okay, so I hope that you see why we needed to break that up, right? It's because the length of the rope is non-constant. It depends on how far the bucket is from the ground. Okay, so what we've seen so far are fairly straightforward computations of work, right? The Hooke's formula gives us a linear function. In this case, we also had a linear function. So let me give you an example where we actually have a nonlinear forcing that's coming in here. And so as with a lot of these problems, it sort of takes a moment to write it all down. So let's go ahead and start with that. So a conical tank is formed by revolving y is equal to 2x with x running between 0 and 5 around the y-axis. So we've got a surface, or sorry, a solid of revolution here. Actually, this could be better characterized as a surface of revolution because this thing is going to be empty. The tank is filled to within 2 feet. So in this case, x and y are going to be measured in feet. So we're using imperial or British units for this, of the top, with olive oil weighing 57 pounds per cubic foot, right? So this is a volume here, or in this, actually, this is a density. And then the question is, how much work does it take to pump oil out, or oil to the rim of the tank? Okay, let's obviously this is a surface of revolution problem, so we need to start with a sketch just so we can see what we're dealing with here. So let me take this on for a second. This is the x-axis, this is my y-axis. Remember, x and y are going to be measured in feet, and we've got y is equal to 2x. And so let's say that up to here is 5. So then on y is equal to 2x, here's the top of my the top of my cone that's being formed. This is 10 right here. And so then, of course, this thing is going to make a nice cone. It'll sort of look like a little ice cream cone. I will attempt to sketch at this, but I'm not sure it's going to be too pretty. I don't think we can ask for much better than that. But in this case, we are revolving around like this. Okay, so the way that we're going to do this is we're going to build up from a Riemann sum, right? Because we don't explicitly have some sort of formula that we can just plug everything into right away. So let's go from the bottom up. And what we're going to do is we're going to think about taking some thin little three-dimensional layer of this oil and calculating the work approximately that is taken to move that thin little layer all the way to the top. So imagine, I take some little layer like this, and it's just some little delta y thickness. So this would be height delta y right here. I can approximate the volume of that layer, and then I can find the work required to move that layer all the way to the top to get it to the rim. So let's say we partition up the height of this thing. So the height of this thing will be determined in terms of y. We're using this vertical variable. So between y and y plus delta y. So this is our usual, say, like yk minus 1 and yk, or yk and yk plus 1, right? They always have a delta, a difference of delta y in between them. So I'm just, instead of putting the subscript k's in here, I'm just going to write y and the next one that's delta y away from it. The slab, so my little piece that I pulled out of this, has volume, has approximate volume. And the reason I'm saying this is approximate is because I'm going to approximate that slab as a perfect cylinder, right? It's the same thing we've been doing over and over and over again when we're doing these volumes. So I'm going to call this, say, delta V. This is the volume of that little slab. Well, this thing is approximately equal to, so the area of the top or bottom of this cylinder multiplied by its thickness. So the area of this thing is going to be pi times the radius squared, and then multiplied by the thickness. Now, the thickness or the height of this thing is delta y. So the question is, what is the radius of this? Well, let's take a look at my picture that I have right here. What we can see is that if I'm at, say, height y right here, then the radius is going to be this distance out to my curve right here. And so the question is, what is that distance? Well, that distance is wherever I am on the x-axis, and I'm lying on the curve, so I can rearrange the expression y equal to 2x to solve for x in terms of y, because the distance is exactly x. So this gives me x, which is equal to y over 2. So what this tells me is that my radius is equal to y over 2, right? It's the distance I've moved along the x-axis to get to the curve. So this gives me pi times y over 2 squared, and then times delta y, which we can clean this up just slightly. Let's do, this becomes pi over 4, so we'll put all the constants down front, y squared delta y. And now we have to ask ourselves, what is the force required to move this, to move this thing? Or so what is the weight of this, is a better way of putting this. Just as a reminder, this is in feet cubed. So we already have a density for the olive oil. The density is given by 57 pounds per cubic foot. Now, each little slab has a volume of pi over 4 times y squared times delta y cubic feet. So if we multiply those two things together, if we follow the units, we're left with just pounds, which is the force. So that gives us force is equal to 57, the density, and then multiplied by pi over 4 y squared delta y, which this doesn't really, it's not going to clean up at all. We're just going to keep all of the constants down front. And then now we can compute the work. Okay, so the work to move this thing, or sorry, the change in the work for this is going to be the distance that this thing needs to get moved. So the distance this thing is moving is from this point on the y-axis all the way up to the rim. So if this right here is distance y, that tells me that this distance is 10 minus y. So that tells me that the work needed to move this little delta V slab which I will call delta W, so we can keep track of this coming from my approximation of my slab. This gives me 57 pi over 4, and then y squared and delta y are in there, and this is also going to be multiplied by that distance, 10 minus y feet. So I'm going to try and keep things looking pretty. So I'll put the linear term first, then I'll put the cubic term or the quadratic term, and then I'll put the delta y term, just so that everything, it's just arranged in ascending order, or if you want to think of it that way. I think it looks nicer this way. Okay, and remember the units for these things are foot-pounds. Okay, so now we have the work required, or the approximate work required to move each one of these thin little slabs when delta y is very, very small. So we're going to do the same thing we've done in almost every single lecture. We're going to see what happens when we let delta y go to 0. And that's the same as saying the number of partitions goes to infinity. So let me just show you what happens here. This essentially tells us that the work is approximately equal to the sum over the number of partitions that we use to break up the y interval here. And then each one of these little terms that we just computed. So 57 pi over 4, and then 10 minus y, y squared. Sorry, let's put a sub k on each one of these just so that everything looks right now. Delta y, and this will be in feet-pounds or foot-pounds. So all I did is I put the yk in there so it's done properly, right? So originally, if I go back here, I just said between y and y plus delta y. It was just saving me a headache of putting yk every single step of the way. But now, we want this to look like a true Riemann sum, so we should start putting those yks back in, right? This is sort of being done informally because you've seen it done a lot. And so taking the limit as n goes to infinity, this is going to give us that the work is equal to the definite integral. We'll talk about the bounds in a moment. And then of this function that we were above taking a Riemann sum of. So 10 minus y, y squared, and then dy. And so the question is, what are the bounds? Well, we start at 0 because that's the bottom of the cone. But if I go back for a moment, look at what it says in the approach to this that's given to us. It says the tank is filled to within 2 feet of the top. So the olive oil doesn't go all the way up to y equal to 10. It goes all the way up to y equal to 8. So you have 2 feet of buffer room at the top of this thing. So that tells us the upper bound here is equal to 8. And now we've got ourselves in a nice situation where we just have a cubic polynomial that we need to integrate. So let me pull the constant 57 pi over 4 out front. Let's expand out this polynomial. So write it as a nice cubic. We integrate this cubic polynomial. This gives us a quartic. So in this case, we get 57 pi over 4, that's floating out front, and then 10 over 3. So the numbers aren't going to be too pretty, but numbers are just numbers. That doesn't bother me at all. Y over 4, and then running from 0 to 8. Now we've got ourselves at a calculator problem, which is just a thing of beauty. And so once you start plugging in 8, the upper bound of 8 and the lower bound of 0 into this thing, I'm going to write this approximately because I'm going to truncate some decimals, but this is about 30,561 foot-pounds of work that needs to be exerted to pull all of that oil up to the rim.